Hello students, welcome back. Today we're going to be continuing talking about the exponential and logarithmic functions, and specifically we'll be working on the logarithmic and exponential equations and models. Okay, so let's recall our previous lesson. So in the previous lesson, we talked about some of the properties of logarithms, and we also learned one important property of one-to-one property and inverse property of logarithms and exponential functions. So today, for the example purposes, we will actually be working and using the properties, one-to-one properties and inverse properties to solve problems. Right, so let's go ahead and get started. So example 1, let's say A. So we have 2 to the power of x is equal to 32. Right, so we trying to find the value of x. Right, so there are multiple ways we can do it. We can either do it through logarithms. Right, we can apply logarithms to both sides of the base 2 to cancel out the values. And once we cancel out the values, we can find the logarithm of 32. Right, so we can do it like this. So we're going to go ahead and apply logarithm base 2 to both sides of 2x is equal to log base 2 of 32. So log base 2 and 2 cancel out, so we just have x is equal to logarithm base 2 of 32. So, and that would be equal to 5. Okay, that's one way we can solve this problem. The other way is to think about 32. So what is 32? So 2x is equal to, so 32 can be also rewritten as 2 to the power of 5. Right, we can remember that 2 to the power of 4 is going to be 2 times 2 times 2 times 2, which is 16. And then if we multiply it by 2 one more time, we're going to get a 32. So that means 2 to the power of 5 is 32. So that means the bases are now equal, so x is equal to 5. Right, so this here we used one-to-one property. Right, one-to-one. And it was easy to use one-to-one because 2 to 32 was actually, could be broken down to a multiple of 2's. Right, sometimes that might not be the case. Right, and we'll see an example. So our future example is going to be the case that we cannot use it. So let's take a look at this example, B. So if we have e to the power of x is equal to 7, right? Remember, Euler's number is 2.718, ... So here we cannot really express 7 as the multiple of e. So here we would actually have to only use this method. So we would have to go ahead and apply the natural log to both sides, and we will have natural log of e to the x is equal to natural log of 7. The natural log and e cancels out, so we have x to equal to a natural logarithm of 7. And that is not, we cannot simplify that, right? We can use calculator to calculate it, but we wouldn't be able to simplify it on our own. So this is, we use the inverse property. Okay, so the inverse property here, and it works just fine. Okay, and then similarly, we can do, let's take a look at problem C. So if we have natural logarithm of x is equal to -5. Okay, so here, how do we find x? Well, for us, in order to find x, we also got to use the inverse property, but it's going to be the inverse property for the exponentials. So we're going to have e to the power on both sides, right? So what do we do to one side? We have to perform identical to the other side. So we will have e to the power of natural logarithm of x is equal to e to the power of -5. So here natural logarithm and e cancels out, right, by the inverse property. So we're going to have x to be equal to e to the -5. Okay, and that's going to be our solution because once again, we cannot simplify it further for this example. Okay, and let's take a look at one more problem. So if we have problem D here, so if we have log of x is equal to -1, right? Remember, log stands for the logarithm of base 10. So what we would have to do, we would have to put everything to the power. So essentially 10 to the power of the left-hand side and 10 to the power of the right-hand side. So we're going to have 10 to the power of log x is equal to 10 to the power of -1. So log and 10 cancels out because we are dealing with the logarithm base 10. So we're going to have that x is equal to 10 to the -1, or the same thing as 1 over 10. All right, perfect. So essentially, let's emphasize, how do we solve those kind of problems? So the strategy to solve those problems is to rewrite the original equation in the form that allows us to use either one-to-one property of either exponential or logarithmic function. Then we can rewrite exponential equation in logarithmic form and apply the inverse property if we need to, and we can rewrite the logarithmic equation in exponential form and apply the inverse property of exponential functions. So either of these three will work for the logarithmic/exponential function. Okay, now let's take a look at more complicated equation. Right, I'm going to give example 2. So we can have something, we want to solve e to the 2x minus 3e to the x plus 2 is equal to 0. So what we want to do is we want to find, we want to rewrite the equation and find the solution, right? We want to find the x value. So here we got to notice, and remember the power rules. So e to the 2x is the same thing as e to the x squared minus 3e to the x plus 2. Okay, so n is equal to 0. So notice, this looks very familiar to us, right? It looks like a quadratic equation. So let's go ahead and try to factor it. So we have something plus something will give us -3, right? -3. And then something times something gives us +2. So we have -2 and -1. Okay, so that means we will have e to the x minus 2 times e to the x minus 1 is equal to 0. Okay, so we have two factors, right? Two factors. So that means in order for us to find a solution, either of those factors can be equal to 0. So let's start with the first one. So e to the x minus 2 is equal to 0. So then we have e to the x is equal to 2. Okay, so we know how to solve that kind of equation. We got to take a natural logarithm from both sides. So here we're going to have that natural logarithm and e cancels out. So we have that x is equal to a natural logarithm of 2. Okay, that's going to be our first solution. Right, it's our first root. Okay, now let's take a look at the second one. So e to the x minus 1 is equal to 0. So e to the x is equal to 1. So now we can go ahead and apply the natural logarithm once again. And we're going to get that x is equal to natural logarithm of 1. But we remember the properties of logarithms, right? What is the property of logarithms? The logarithm of 1 is always going to be 0. The answer here is 0. So x is equal to 0. That's our second solution. All right. And that makes sense. We had a quadratic equation, right? And we got two solutions. So the way we can do it, we can plug it in and check, and they actually are going to be matching. Okay. Now, of course, we could also, let's go ahead and do logarithmic equation, right? We can do logarithmic equations. So an example, let's go ahead and do a simple example here. So example 3. So we have 5 plus 2 natural logarithm of x is equal to, right, we want to find x. So the first step is going to be for us to subtract 5 from both sides. So we're going to have 2 natural logarithm of x is equal to 1, -1. And then let's go ahead and divide both sides by 2. So 2 and 2 cancel out. So we have natural logarithm of x is equal to -1/2. And now how do we get rid of logarithm? We have to put the left side, essentially e to the power of the left side and e to the power of the right side. So and then e and logarithm cancels out. So we have x to be equal to e to the -1/2. And that's going to be our solution for this problem. Okay, perfect. And now let's go ahead and take a look at more sophisticated problem. So it's going to have example 4. Example 4. So we have a logarithm of 5x plus logarithm of x minus 1 is equal to 2. Okay, so let's recall that we can use the properties of logarithms to simplify that. So let's go ahead and try to simplify the left-hand side. So we have a logarithm base 10 and logarithm base 10. So if we adding the two logarithms with the same base, we're going to multiply the internal part of the logarithm. So we're going to have logarithm of 5x times x minus 1, and that's equal to 2. Okay, now, since we cannot simplify any further, we have to go ahead and put 10 to the power of the left-hand side and 10 to the power of the right-hand side. So logarithm and 10 cancels out, so we're going to have 5x times x minus 1 is equal to 10 squared. Okay, so on the left-hand side, let's simplify. Let's distribute the left-hand side, so we're going to have 5x squared minus 5x, and that's going to be equal to 100. Now let's divide both sides by 5. We divide by 5 each term, because that's our common factor here. And let's see, we're going to get x squared minus x is equal to 20. So if we subtract 20 from both sides, we're going to have x squared minus x minus 20 is equal to 0. Okay, now let's go ahead and solve this quadratic equation. And we're going to solve it by factoring, right? By factoring. So something plus something is -1, something times something is -20. So we can think about -5 and 4, right? Because -5 plus 4 is -1, and -5 times 4 is -20. So we will have x minus 5 times x plus 4 is equal to 0. So once again, we're going to have two solutions. Solution 1 is x minus 5 is equal to 0. So x must be equal to 5. And x plus 4 is equal to 0. So x must be equal to -4. All right, perfect. And that's going to be our solution to this problem. Okay, now let's go ahead and recall that last time we learned about the compounded interest and we learned some formulas. So let's actually take a look at some of the applicational problems. Right, application problems. So I'm going to say example 6. Here, we're going to have the following. Let's talk about the compounded interest problem. So let's say that you invest $500 at an annual interest rate of 6.75%, and it's compounded continuously. How long will it take your money to double? Okay, so let's recall. So the solution, let's recall the formula. Remember the formula, A is equal to the principal times e to the power of RT, where R is the rate, T is the time. Okay, so in our case, right, for our problem, our equation is A is equal to 500 times e to the power. So R is 6.75 divided by 100, which is going to be equal to 0.0675. Okay, so we're going to have e to the power of 0.0675 e. All right, so, and we want to find the time, right? How long will it take when this amount A is doubled our principal amount? So that means 500 times e to the 0.0675 times t, which is our unknown, is equal to 1,000, right? That's what we're looking when it's actually doubled. So let's go ahead and solve this problem. So we're going to divide both sides by 500. So 500 and 500 cancel out. So we have that e to the power of 0.0675 times t is equal to 2. All right. Now, let's go ahead and take the natural logarithm on both sides. So we're going to have natural logarithm and e cancels out. So we have 0.0675 times t is equal to natural logarithm of 2. Okay. So that means t is equal to natural logarithm of 2 divided by 0.0675. And if we plug in a calculator, we're going to get roughly 10.27 years. Right, so in over 10 years, the principal money which we put for the 6.75% which annual interest compounded continuously, we will double it only in 10 years. All right, perfect. Now, so since we did some of the application problem, which was based on the last time's material, let's go ahead and move on to the models of the exponential and logarithmic equations. So, right, so models. So let's go ahead and take a look at 5 most used models in exponentials and logarithms. So here it is. Number 1 is going to be the exponential growth model, right? So it gives us growth. It can be a population growth, it can be a bacteria growth. So number 2 is exponential decay model. So it's very similar to the growth model, but b is negative, right? So that's a decay model. Then the Gaussian model. The Gaussian model is used in statistics. You probably have heard before a Gaussian distribution. Every time when the survey is done or when some kind of statistics is taken, we can sometimes approximate it by using a Gaussian model or a Gaussian distribution, right? And if you do not know that, you can check out a video on the statistics that you will be able to find, link in the description. All right, then the logistics growth model, which is also a growth model. So that model is used for population, right? Oftentimes, this model this equation can model the population of the city or a state during certain years if you take enough data points during those years. So there are multiple things that it can be used for. Okay, and the logarithmic models, right? So logarithmic models, in terms of the base of natural logarithm of e and the base 10 logarithm. Okay, so and the way the equations would look like, right? So we just wrote some equations, we called them, but let's actually take a look at how would those 5 equations look like. Or here essentially here how it would look like. So the first equation is the exponential growth model, then exponential decay model. So here we have essentially 1, 2, 3, 4, and both of them would be 5. Okay, so the exponential growth model, e to the x. The exponential decay model, e to the negative x. Gaussian model is e to the negative x squared, right? So this is a Gaussian distribution. Then the exponential growth model, here's an example. So it would be approaching, population would be approaching a value of 3, for example. Then natural logarithmic model and common logarithmic model, right? Which is base 10 model. Okay, so now what we can do is we can solve some problems. And let's go ahead and solve some of them. So here's going to be our first problem. Our first problem is a US retail e-commerce sales in $1 billion from 2012 through 2018 are shown in a table on the right side. A scatter plot of the data is shown at the right. Here it is. So we are given the data by year and the amount of sales in billion of dollars. So an exponential growth model for the data is as following, where S is the amount of sales in billion of dollars and T represents the year, with T as corresponds to 2012, and essentially we would go up to 18. Right, so compare the values found using the model with the amounts shown in the table. According to the model, in what year were the sales approximately 690 billions? Okay, so here essentially we wanna find in what year the sales were 690 billions. So what future essentially year that will be? So okay, essentially we want to say, well, we're given an equation. S is equal to 44.73 times e to the power of 0.1368. And we're given that S is equal to 690, right? So we're trying to find the time, right, when it actually happens. Okay, so we're going to equate those two numbers. So we're going to have 690 is equal to 44.73 times e to the 0.1368 times e. Okay, so now we're going to go ahead and divide both sides by 44.73. 44.3. So 44 and 73 cancels out here. So we're going to have 690 divided by 44.73. and that's equal to e to the power of 0.1368 times e. And now we take a logarithm to both sides, right, just as we did previously. And now we can have natural logarithm of 690 over 44.73 parentheses, and that is equal to 0.1368 times t. So we have to divide both sides by that number. So t is equal to natural logarithm of 690 over 44.23 divided by 0.1368. And if we plug in that in calculator, we will get roughly 20, right? Which means that it's in 2020. We will hit 690 billion. Okay, perfect. So that's essentially how we would solve those kind of problems. All right. Now, let's go ahead and take a look at a population growth model. So for population growth model, we will have the following problem. Here it is. So in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? Okay, so what we have is we have two equations, right? Let's remember, we have two equations. So 100 is equal to a times e to the 2b, right? Where a and b are constants that we do not know. And then in 4 days, we know that it's 300 is equal to a times e to the power of 4b. Okay, so that's how we set up the equations. So now the first thing is, let's write the first equation. So by first equation, let's express a. So a is equal to 100 divided by e to the 2b, right? Because I divided both sides by 2e to the 2b. And now let's go ahead and plug that in into this equation. So we're going to have 300 is equal to 100 over e to the 2b times e to the 4b. Now we can go ahead and simplify, right, by the rules of powers. So we're going to have 300 is equal to 100 times e to the 4b minus 2b. So 300 is equal to 100 times e to the 2b. Now let's go ahead and divide both sides by 100. So we will have 300 divided by 100, that's 3, is equal to e to the 2b. Okay, so now we can go ahead and take a natural logarithm on both sides. So we're going to have ln of 3 is equal to 2b. So then divide both sides by 2. We will get that b is equal to 1/2 natural logarithm of 3, right? Okay, so we solved that. Now let's go ahead and move on to a, right? So a was 100 divided by e to the 2b. So if we plug in our b constant, we're going to have 100 over e to the 2 times 1/2 natural logarithm of 3. So 2 and 1/2 cancel out, so we have 100 over e to the ln of 3, which is equal to, so ln and e cancels out, so we have 100 over 3, which is approximately equal to 33.33. Okay, so that means we will have our equation here, right? Y is equal to, so it's going to be a times e to the power of bt. So that's equal to 100 over 3 times e to the 1/2 ln of 3 times, all right? And that would be our growth equation for this problem. Okay, perfect. Now we can also similarly work with the decay, right? The decay models. So let's take a look at the carbon dating of fossils. So we're going to take a look at this example. So we have the ratio of carbon 14 to carbon 12 is a newly discovered fossil. So, and the ratio is 1 to 10 to the power of 13. So what we want to do is we want to estimate the age of a fossil. Okay, and so how do we know that? How do we know that? And here, let's go ahead and kind of have a quick review of what would be the model for such. Let's go ahead and give a little background here. So we can have that in living organic material, the ratio of number of radioactive carbon isotopes to number of non-radioactive carbon isotopes is about 1 to 10 to the 12, right? So when that happens, essentially we can calculate the half-life of when the material is breaking down, and the half-life of that is 5,700 years, right? So oftentimes the scientists, biologists, and physicists use half-life times because some of the components are decaying at the very, very long time, so especially radioactive components. So we're going to be using this equation, right? This is a carbon dating model, right? This is essentially, we're going to be using that equation. So we know that R is equal to this, so we're going to apply our R. So our given model, right? This is the model. And what we can say is, okay, well, we're going to plug in, we have that 1 over 10 to the 12, e to the negative t over 8,223 is equal to R, which is equal to 1 over 10 to the 13. Okay, perfect. So now let's go ahead and simplify. The first thing we're going to do is we're going to multiply both sides by 10 to the 12. Okay, so 10 to the 12, we will have e to the negative t over 8,223, which is equal to 1 over 10. Okay, now let's go ahead and take natural logarithm from both sides, and we will have negative e over 8,223 is equal to natural logarithm of 1 over 10. All right, so let's remember the properties of logarithm. So negative t over 8,223 is equal to, so this is the same thing as natural logarithm of 10 to the negative 1, which is equal to negative 1 times natural logarithm of 10, which is simply equal to negative logarithm of 10. So we have negative t over 8,223 is equal to negative ln of 10. So negative and negative cancels out. So we have t over 8,223 is equal to natural logarithm of 10. And that means that t is equal to 8,223 times logarithm of 10. And if we plug that in the calculator, we're going to get 18,934 years. So almost 19,000 years. So that fossil that we found is almost 19,000 years. All right, perfect. Now, let's go ahead and do the Gaussian model. So essentially, for a Gaussian model, we're just gonna talk over this example. We're gonna see the model and how it looks like, and we're gonna discuss it. So we have the SAT or Scholastic Aptitude Test, which is the mathematics. We were doing the mathematics course for U.S. high school graduates in 2019, roughly followed by the following normal distribution. So normal distribution is essentially a bell curve, right? This is what we used in statistics. And essentially here would be the graph of the SAT scores, right? That would be the SAT scores. That would be the model that is provided right here, where X is the SAT score for mathematics. And we can use the graphing utilities to graph this function, which is here it is. And here, essentially, we are looking for the area under the curve, right? So the area under the curve tells us what's the percentage of people, right, who scored above a certain number, right? So the higher the percentiles are, this is essentially the percentile, the better it is the score, right? If you're all the way right here, you scored 800 almost, right? Or like 799. So as the lowest one is 200, the highest one is 800. So that's going to be the domain of that equation, right? The X is going to be the scores between 200 and 800. All right, you can use Desmos to graph this equation, right? To graph this equation and to solve it and to find the values for it. Meanwhile, we can go ahead and move on to the logistic equation. Right, and specifically logistics equations, as we previously talked about it, is we can use it for population growth or decay, or we can use it as the spread of viruses. So, and actually, let's take a look at a spread of viruses example. So on a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. So the spread of the virus is modeled by the following equation. So here it is, where y is the total number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. Okay, so how many students are infected after 5 days? Okay, so essentially, after 5 days, what do we want to do is we just want to plug in. So for part A, what do we want to do is we want to do y of 5 is equal to 5,000 over 1 plus 4,909 e to the negative 0.8 times 5. Okay, so that is going to be equal to 5,000 over 1 plus 4,999 times e to the negative 4, which will give us roughly 54 students, right? So after 5 days, only 54 students are infected. Now for part B. After how many days will the college cancel classes? Okay, so we know that we need half a student, or 40% of the students, right? So what is 40%? So 40 over 100 times 5,000, which would give us, so it's the same thing as 40 times 50, which is going to give us 2,000. So we got to have at least 2,000 students sick. So let's find out. So we have 2,000 is equal to 5,000 over 1 plus 4,999 times e to the negative 0. Right, so we want to solve for t. So let's go ahead and multiply both sides by the denominator. So we're going to have 2,000 times 1 plus 4,909 times e to the negative 0.8 t equal to 5,000. So if we divide both sides by 2,000, we're going to get that 1 plus 4,999 times e is equal to 2.5. Subtracting 1 from both sides, we're going to get 4,999 times e negative 0.8 is equal to 1.5. So now we can divide both sides by 4,909. So e to the negative 0.8 t is equal to 1.5 divided by 4,909. Now we can go ahead and apply the logarithms to both sides, the natural logarithm. So we're going to have the negative 0.8 t is equal to logarithm of 1.5 over 4,999. Okay, and so t will be equal to negative 1 over 0.8, because we divided both sides by negative 0.8, times natural logarithm of 1.5 over 4,999. So if we simplify it, we're going to get roughly 10.14 days, right? So after 10 days, there are going to be at least 40 students who are infected. So the college will have to cancel classes after 10 days. All right. And then the last part is going to be the logarithmic models, right? So the last model that we're doing today is going to be the logarithmic model. And so here is an example of one of the logarithmic models. So the sound level, right? So the level of sound in decibels is intensity of I in watts per square meter is as following, where I naught represents the faintest sound that can be heard by human ear and is approximately equal to 10 to the negative 12 watt per square meter. Okay, so now let's go ahead and take a look at a problem. We have the following. You and your roommate are playing music on your soundbars at the same time and at the same intensity. How much louder is the music when both soundbars are playing than just one sound is playing? Okay, So essentially, we're going to have, let's do this. So we're going to say that let beta 1 is going to be sound of one soundbar. So soundbar. And then beta 2 sound of two soundbars. Okay, so that means beta 1 is going to be equal to 10 times logarithm base 10 of I over 10 to the negative 12. And beta 2 is going to be equal to 10 times logarithm of 2i over 10 to the negative 12, where I is essentially the sound of a soundbar, right? And 2i because we have two of them now. So now let's go ahead and simplify. So what we would do? We would try to find how much more louder would it be. So beta 2 minus beta 1, which is equal to 10 log base 10 of 2i over 10 to the negative 12 minus 10 of log I over 10 to the negative 12. So that's beta 1. So that is equal to, so 10 logarithm base 10 of 2 times I over 10 to the 12 minus log base 10 of I over 10 to the negative 12. So from the first logarithm, let's go ahead and factor out the 2 and use the logarithmic rules. So we're going to have 10 times logarithm base 10 of 2 plus logarithm of I over 10 to the negative 12 minus logarithm of I over 10 to the negative 12. So clearly, these two are going to cancel out. And we're going to be left with just logarithm of base 10 of 2 multiplied by 10. So we're left with 10 times logarithm of 2, which if we calculate, going to give us 3 decibels. So the music is going to be about 3 decibels louder when both of the soundbars are combined together. All right, perfect. So that would be it for today's lesson. Thank you, and I'll see you all next time.